We've studied many different ways to approach limits. We've learned about L'Hopital's rule for indeterminate forms. If we have a graph, we can evaluate the limit visually, and we can also use direct substitution to evaluate our limits. Another technique that we can use is looking at the functions themselves and determining which one grows faster. What is their rate of growth? That comes with knowing our parent functions and how functions behave. So this is something that you may remember. If not, we're going to review right now. But it does come up with rational functions in a previous course. So let's look at this example. So suppose you have this quotient of functions. If the function on top, the numerator, grows faster than the function on the bottom, then the overall limit is headed towards positive infinity. If, however, the denominator function, the bottom function, is growing faster and the numerator is growing slower, then the limit is actually approaching 0. Now, these are the limits as x approaches positive infinity, so keep that in mind. The last one says, well, what if they grow at the same rate? Well, the limit as x approaches positive infinity, it's not going to go to infinity, it's not going to go to 0, it's actually going to go to some number that's not 0. And that's if they grow the same. So this language may sound familiar to you, although the notation may be not as familiar. But we have studied these with rational functions. So I've given you 3 functions to consider: x squared, e to the x, and 5x squared. Let's look at the first example. This is the limit as x approaches positive infinity of x squared divided by e to the x. Now let's think about our parent functions. X squared, that's just a nice quadratic, right? E to the x, though, that's an exponential. Which one grows faster? The exponential does. Because the denominator grows faster than the numerator, then the overall function, because of the limit, will approach 0. Let's look at the next example. We have the limit as x approaches positive infinity. This time it's e to the x divided by x squared. Well, e to the x is an exponential, so we know it looks like that. And 5x squared, that's just a quadratic function that has been vertically stretched by 5. So which one's growing faster? Well, again, the exponential will always outgrow a polynomial. So because the numerator is growing faster over the denominator, now this overall limit is headed towards positive infinity. So if you look at these 2 examples, this is interesting. We have an exponential and a polynomial. In both cases, the exponential is faster than the polynomial, but because of its location, it made the limit either go to 0 if it was in the denominator, or approach positive infinity if it was in the numerator. So again, the location of the functions really matters. Don't automatically assume just because there's an exponential function in there, for example, it's automatically going to be infinity or 0. The location is important. Let's look at our last example. So this time we have the limit as x approaches positive infinity of x squared divided by 5x squared. Well, this is a quadratic, and this is also a quadratic. So since these are both parabolas, they essentially have the same growth rate. So what's the limit? It goes to some value, correct? Well, if you remember from your rational functions, notice the degrees are the same. When the degrees are the same, we use the leading coefficients to determine the limit.